Tim, take it away.
So, what even is data engineering? Let's find out. Who am I? I'm Tim van Keer. I am a DataOps enthusiast, and this basically means that I like working with cutting edge data technologies. Um, I like working with people who work with data because I believe that only together we can build better tools and better tech stuff. And that's what is very prevalent in DataOps. I also more formally do Dev and DataOps at Fullstack, and Fullstack is a wonderful company here in the Netherlands doing all kinds of cloud native stuff, microservices, Kubernetes architectures, and everything that runs on top of Kubernetes. Um, we're a bunch of nerds. We grow really fast. Last time here at DYJ, I had the full posse, the full company with me as well, which was like 5 guys. Now we are 40 guys, so I couldn't bring anybody along. Also, I'm a proud member of the Data on Kubernetes community. This is a community for the betterment of data on Kubernetes. People might think you cannot do data on Kubernetes, but you can, so it's not just for stateless workloads. It's very cool community. Check them out if you like doing Kubernetes stuff. And now on to the good stuff. So what did I do for these past 3 years? I figured out what data engineering even is, because up until 3 years ago, I did not know. Basically, there was a problem at one of our clients. They had problems with the data pipeline. I did DevOps, and they contacted me, hey, can you help us out? And I basically turned this into this. And along the way, I figured out what data engineering even is. So the problem that they had was they had a data pipeline that was ingesting data via a Python application running on a virtual machine. That data went to an internal data warehouse. That data then went to another server that did something with R. And then that data went over to another data warehouse, BigQuery. Was error prone. There was no version control whatsoever. There was also no quality assurance. Lots of things were wrong with it. Lots of things that I knew how to fix because this was all DevOps stuff. But I did not really touch upon the data engineering specifics, or basically moving the data around. And then 3 years later, we turned it into a nice data platform with all kinds of data engineering goodies inside. This is actually already a pretty old slide from, I think, a year ago. And nowadays, our ecosystem is much, much wider already. We also do machine learning now. We have also data platform components on Azure. So this is just a small bit. So I want to show you guys and gals a little bit what you can do with data engineering, or some use cases in which data engineering is a pivotal part. And the first one is pretty boring, personally. It's dashboards and reports. So we need data engineering here to make sure that we have correct data available to do analytics for dashboarding and reporting. So we have source systems, then we have something in between, which is data engineering, and then we have dashboards and reports as output. Pretty boring if you ask me, but what's more cool is that we can also do more interesting things where data engineering is an enabler. And one of the things here is, for example, automated product rank listing. And what we try to do here in this use case is we try to change the way products are shown to our end users based on certain data in our system. For example, we might have different products of the same type, but they one has a higher markup, so higher revenue for us, but maybe it's a product that our customers don't like seeing. Then using some analysis, we can get a data set that, when fed back into a search engine, relists where certain products are without actually giving that our customers a bad idea that they are seeing a product that they don't want. And they actually get shown a product that gives us a higher revenue. This interaction from the user with this automated product ranking also turns back into a new data set. That data set feeds back into our system. That gets used for analysis again. That gets shown to our end user. the end user interacts with that, and that feeds back into a system again. So we get an automated system doing analytics, which generates value immediately. And then the third use case is continuous machine learning. So here also we need data engineering. We need data engineering to be able to supply correct and reliable data to a machine learning algorithms so they can make the correct forecasts. And an example of this could maybe be maybe we measure how many people are in a certain street, like with the corona things, and then we correlate that with maybe some weather data and maybe some public holiday data, and then we try to make a forecast. Hey, how busy is it going to be in the street? Do we want to use 1 meter, 2 meters, 3 meters, 4 meters distance? So we try to forecast based on that. And for that, for our algorithm to do that, we need to feed it correct data. Because if we don't feed it correct data, we'll get the wrong forecast and we'll take the wrong actions. So that's pretty cool. Continuous machine learning, automated product ranking is also pretty cool. Dashboard and reports, it's kind of a given when you have data or want to do analytics. So what data engineering does is it enables generating value from insight. That's what data engineering enables. It enables good data so that people can do analytics, so that people can create insight, feed that back in our systems, create value. And I kind of envision it a little bit like this. Like the house of data, where we have a bottom layer, which is our infrastructure. We have 3 pillars, and then we have the roof on top. And this translates to this. So we have 1 pillar, data sources, generation, which is all of our raw data sources, or maybe not just raw data sources. It's basically just data sources. So data sets in databases, raw files somewhere, maybe on somebody's hard drive, logging and metrics data from our applications and the services in our landscape. These are all examples of data sources. And then on the other end, we have insight creation. So usually BI, business intelligence specialists or data scientists will use our data to create insight, to create new data sets based on a SQL query. Maybe they will use some Python scripts to do some analytics. Maybe they'll create a dashboard, who knows, right? Maybe they'll use Excel and CSV files. God forbid, I can't even say CSV files, so hard. And then in the middle we have data engineering. And data engineering is what ties this together. So data engineering enables that we get the correct data available for generating insight. And if one of those pillars fails or does not work correctly, we have no insight, or maybe we have insight, but we do not have the correct insight. So we have unreliable insight, and then our house comes tumbling down. And if we don't have the correct systems in place, we won't even know that this is happening. So what hurts? From the end user's perspective. So from the end user's perspective, when living in a data world, it really hurts to not know what data is out there. So they don't even know what data to use to get to a certain analysis, to a certain insight. Maybe they'll have to ask around, hey, do you know if this and this data is there and if I can use it? And then that person will say, oh yeah, maybe you should talk to that guy, and then that guy points them to somebody else, and then that somebody else is no longer working for the company, and the knowledge is gone. Not knowing what data means. So maybe the data is there, but it's just numbers, it's just strings with some fields, with some columns. There's no descriptions, there's no description about the data set as a whole. Nobody knows when it was last updated, if it's even used anymore, if it's even relevant. And this really hurts because we cannot create insight when we don't know what data means. And the third one is data being unreliable. So it's kind of a culmination of the top two, right? Data is unreliable when we don't know where it is, when we don't know what it means, when we don't know if it's still used, if it's still updated. This really hurts from an end user perspective. This sucks. This is what we have to solve using data engineering. What hurts from a data engineer's perspective? It's the same thing, because this is the problem we are trying to solve. We need to supply reliable and meaningful data for our end users. So personally, if I don't know what data is in my system, that hurts me. If I don't know what data means in my system, that hurts me as well. I mean, I don't even know how to use it because I'm not an analyst, I'm not a data scientist. But if I don't know what data means in my system, that just sucks because I don't have a describing system. And data being unreliable kind of speaks for itself. Of course, there's many more things that hurt a data engineer. CSV files, CSV files, CSV files. Who of you uses CSV files? Stop using CSV files, use something else. Okay, so the power of data engineering, this is like the crew. The power of data engineering comes from being able to supply reliable and meaningful data in a correct and timely manner. If we do this, we are good. This is what we need to do. So let's fit data engineering into these use cases. Dashboard and reports. This is like the base thing. This is the thing we start doing when data engineering. When we don't have dashboards and reports and data engineering in place, we want to create dashboards and reports. And this is what we need to do. So we need to ingest data from source systems. Then we need to clean and enrich that data so that we can use it for analysis. Then we need to catalog and describe this data. And then we need to make data available. This is the base of what we need to do to get to dashboarding and reporting. And I did not put dashboarding and reporting in here because that's not really a data engineer's task, at least not mine. I don't know anything about creating dashboards, well, maybe a little bit. But I'm not a data scientist. I care about these things. But yeah, also, what I think personally is really important that we try to build tools so that end users can do the above things themselves. So that if there's maybe an interesting piece of data they want to ingest, that they want to clean, that they want to transform, they can do that themselves. And of course, this changes varying on the degree of skill and the type of end user you have. But let's try to enable people to do the things themselves, right? Otherwise, they always come to you with silly little things, which they might be able to do themselves. So the first step, ingesting data from source systems. Here we have an example of raw data. So we have here raw sales data, and we have here some Google Analytics data. I don't even know if this is correct Google Analytics data. I think it is. Is it? Does anybody know? No? Okay, well, let's just assume this is correct Google Analytics data. So we have our raw sales data, we have a customer ID there, and we also tag the customer ID in our front end if a user has logged in, so we can track whatever he does on the front end. And then we ingest this data and we output it into our data warehouse. Something we also do is we cleanse data. So we ensure that data adheres to a certain standard that might be useful or valuable down the line for our analysis. In this case, maybe we sometimes don't have a customer ID because it's an unknown customer, but the customer is not logged in or registered in our system. And we don't care about records where we don't have a customer ID because we cannot use it for some analysis that we want to do. So then we cleanse those records from our data, and then this becomes a new data set. So cleansed sales data. And this also goes into the data warehouse. Next up, we have enriched data. So we first have our cleansed data, and now we want to enrich it. We want to enrich it with our Google Analytics data so that we get a data set that is ready for analysis. In this case, we want to track or do analytics on sales from advertising. We have this advertising data from our front end, from our Google Analytics. We add that data based on customer ID to our cleansed sales data, or we create a new data set derived from those two. And now we have a data set that you can use for maybe tracking if users, via which ad campaign users come in, and if they are often or if they are not hitting products in an ad campaign when they are maybe in their basket or in their sale. Next up, we catalog and describe this data. So for me, it's a thing that is often overlooked, but it's the most important thing in data engineering. It's describing what the data means. So what does a data set mean? What can you use it for? Where does it come from? When was it last modified? What kind of data is it? Who is managing the data? Who is owning the data set? So in case you do need to ask somebody, you can go directly to the correct person or the correct team. Also document your model. So what are the columns? What are the fields? What are their types? And not just the types, but also what do the fields mean? So if it's a sales type, it can only be one of online, offline, or a side hustle. And you can also use this further down the line for automation and for data quality testing. If you just put this information in your model, if you just describe what your data is and what your data means. And we put that in a data catalog so that other people can find data that they need in our systems. And then the last step here is to make this data available to our end users. And how do they use it? That's how you supply it. That's personally my opinion. If they want to use a certain dashboarding tool, if they want to have a data set, the data set in SQL, if they want to have, God forbid, CSV files, then you supply them CSV files. So a stream of data that they consume, if they want to have a data stream, even though it's not really useful because it's batch data and it comes once a week, if they want to have it in a data stream the moment it arrives, then you just do that. That's my point of view. Try to make it simple for your end users. Next use case, the automated product rank listing. So here we do all the previous steps. That's the base for our data engineering platform, for the thing we do in data engineering. And what's different here is that a data scientist or analyst then creates insight that feeds back into our systems, in this case our search engine. And then the interaction from our end user with this generates a new insight, a new data set that feeds back into our system that we use again in our analysis, so we get an automated system. And we run this analysis every night, we output it, and then we load it into search infrastructure, like I just said. And for this we use a data workflow. So a data workflow is the steps we need to take to get from point A to point B. So which source data we need to ingest, what we need to do with it, do we need to cleanse it, do we need to transform it. Then maybe we have a bit of analysis, so then the data scientist comes in, they say, hey, I have this Python script or this SQL query that generates this insight, and then we add that to the workflow as well. And then the workflow is what we interpret and run. Usually a workflow, it's not always the case, but what I find out is that usually it's configured using programming language, Python in our example. But a workflow could be as simple as just some bash commands tied together. Those can also be steps in your workflow. Take a file, process a file, output a file. That's already a data pipeline. That's already a workflow. So in this case, we check if dependencies are met. Is our raw data available? Is it up to date? So are we using the latest data for our analysis? Then we run the analysis, so whatever the data scientist provides, SQL query, Python script, whatever. Then a very important one, which is not really standard in data engineering, but should be, is testing the output. So not just testing the components of our infrastructure, testing our code, but also testing what happens in the data. So in this case, we probably have the data scientist. They know what the output should be like. They know certain KPIs, and they should log those KPIs for us, so we can build tests around that. So whenever we run this analysis, we know if it's correct, so we don't feed unreliable data back into our system. And this nearly never happens, which is really stupid. Then we write the output to a data set, and then we upload that data set to our search infrastructure. And then the next day, we do it all over again, automated. Next use case, continuous machine learning. So I'm only going to touch briefly upon this one. It's a lot of the previous steps. Again, who would have thought? But now our analysis algorithm trains itself based on good, clean, usable data. So again, we made the data available in a reliable and correct way, so that the algorithm that was developed by a data scientist can continuously train itself on correct data. Because if we do not do that, and if we do not have quality gates in place to test and verify that data, we get crap. We get a forecast or an output or prediction from a model that we don't know is correct. It might look correct, but we can't validate that that is correct. We need to validate for every step along the way. So data engineering is really important here. Again, good, clean, usable, and reliable data. That's what our model needs, so that is what we need to provide. Data engineering tools is the next section. And I just briefly want to touch upon some of the concepts of things you've already heard me talk about in other slides, like data warehouse, data workflows, stuff like that. I basically want to touch upon some common core infrastructure components, the concepts around them, so what they mean, what you usually encounter. So what is a data warehouse even, right? So it's just really big database. That's what a data warehouse is, and it's the core component of data engineering infrastructure. It usually works with SQL, some other kinds of relational data, and where this differs from a transactional SQL database that you would use for making quick changes to records, making quick changes to tables, and then providing the output from that back to your end users with low latency input. That's not the case here, because we have very large volumes of data that we want to churn, that we want to run analytics over. Could be terabytes or more and more and more, so we don't have this latency for our end users. But that's becoming more and more important to do this analysis as fast as possible. And that's also that you see with the major cloud vendors, they are all separating compute from storage, so that you can basically run your analytics faster. You can scale out the compute depending on the kind of query you are running, so you can get your output, your insight faster. And this is, I mean, the major cloud providers are already front runners in this, but this is going to be the new standard. Databases where compute is completely separated from storage. Then we have the data model. So the data model is everything describing a data object in our system. It's a centralized place where we describe what a data thing looks like. What you can use it for, where it comes from, how it is created. Maybe it is the definition of a table in your data warehouse with a schema and a description and an owner, and maybe also the steps you need to take to build the data. And the model initially, at least that's what I think, is for people to interpret. So maybe this also has a certain definition of what revenue is for you or for your company or for your business. So it's for people to interpret. It's also good for in the data catalog, but it's also an entry point for further automation. So if you have something that is describing what a data object looks like, what the steps are you need to take to get to the certain data object, then you can have your systems interpret that model and then build the data pipelines themselves, build the data objects in the database itself, build the tables, output data about it to the data catalog. So it can serve as an entry point for building the data objects in your system as well, not just describing them. Next up, data pipelines. And I put data pipelines here, but it's also a little bit data workflows. So it's basically the steps to get your data from point A to point B. And the data pipeline is usually the thing, it's like the runtime environment. The thing that actually runs is the data pipeline. Yeah, so basically it's also the steps you take to get from point A to point B. Data pipeline can be very simple, can also be very complex. Yeah, data lake. That's also interesting. It's a large volume of data as files. So we might not only have relational or structured data, we might also have video images, video files, images, maybe some audio files, all different types of data, structured and unstructured. And we also need a place to store them. And this comes in the form of a data lake. And the data lake is basically blob storage on which we store files, and then we have an abstraction layer on top of that. And this abstraction layer provides us with indexing, with search, and maybe also query functionality, and some other metadata that describes the files, that generates a certain standard on top of them, that makes it easy for us to find the data we are looking for. What's also nice is that with a lot of the current data warehouses, you can have your files be the source of your tables. So you can make a sort of a managed table in your data warehouse based on files in your data lake, so that you can use the power of your data warehouse for doing queries and analysis, but still have the scale out flexibility of a data lake of just files on blob storage. Workflow orchestrator, also very important. This is what actually runs the workflows, runs the data pipelines. Runs them every day, runs them every week, runs them once a year, runs them maybe continuously. And this workflow orchestrator interprets our workflows, spins up our data pipelines. There's usually also a little bit of monitoring and logging around it. So anything that I as a data engineer would need to monitor and manage the flow of data in my system, that's usually in the workflow orchestrator. But it can also be very simple. I mean, if you have some bash scripts and you tie them together using cron, that's also already scheduling of your workflows. So it doesn't have to be complicated. Data catalog, often overlooked. If you don't do this from the start, you're going to have a bad time, because then you are talking more about doing a data catalog than actually implementing a data catalog. So it holds the information about what data there is in our systems, what the data can be used for, who is maybe using the data. So if it's like a really popular data set, or maybe it's a data set that's never used, so it can be an indicator that you don't want to ingest it anymore, or don't want to process that data anymore. That's all the stuff that goes in the data catalog. So data about data in our systems. And try to get every piece of data in there. You might not know what people actually want to use, and they might not know as well. So let them find it. Programming languages, also something that we use in data engineering. All kinds of programming languages, basically. Go, Java, Python, Rust maybe, but usually Python or Scala, which I've never seen in my life, to be honest, but other people probably have. So we use it for analysis, we use it for scripting, we use it for writing data workflows, we use it for notebooks, which is usually something that data scientists use, and we use it for spinning up data pipelines, for building all kinds of scripts around the things we do within our data engineering world. And there's lots of really, really good established data engineering and analytics libraries for both Python and Scala. That's why it's a really important, really popular language. And then there's the rest. Git, version control, CI/CD, infrastructure as code, hundreds and hundreds of databases, machine learning, REST APIs, Kubernetes, YAML, lots of YAML, monitoring and logging frameworks. This is what we all use as well. For me, a data engineer is also a data platform engineer. They're also a software engineer. They need to use correct software engineering practices, software engineering hygiene around data and around basically everything they do. And for this, you use version control, you use tests, you use CI/CD, etc., etc. And we do this to build robust systems, because that's what we want to have. We want to have a robust system for our end users. So we can supply reliable and meaningful data in a correct and timely manner. That's the thing we try to do. And in the full landscape, kind of looks a little bit like this. So this is a picture I drew of a data platform. We have our source systems, right? So it's streaming data, it's a message bus, it's a data set, it's files, whatever. And then this data goes through data pipelines. And these data pipelines run maybe once a week, or maybe they run every day or every 10 minutes, or maybe they run real time. They're actually streaming data pipelines. And our pipelines are orchestrated by a workflow orchestrator. And we have data engineers and data scientists using Git, using version control, using tests, using Python or whatever tool they use to write their workflows. This gets interpreted by the workflow orchestrator, spins up the data pipelines. And the data pipelines output the data in the data warehouse. And they also output the data about the data into the data catalog. If it's fresh, we spin up the data pipeline, which data pipeline it is, where does the data come from, what does it mean, etc., etc. And then on the other hand, we have the business analyst who's checking the data catalog. Hey, is there some data in there that I might use for my analysis? Yes, there is. Well, he's also writing his analytics. This is perfect world, by the way, right? It's usually not the case, but business analyst also uses version control, and they generate some dashboards and reporting that the business uses, and the business likes that because they can see that they are making more money. This also feeds back into the system. So this becomes its own data sets, its own data source. Maybe there's some dashboards and reports that we build that nobody uses. Why do we build them then? Right? This is also metrics that we can export and that we can use for analysis again. And then maybe we should just deprecate certain dashboards and data sets. And then we also have our systems using our insight. So this is maybe a machine learning framework that is serving an API that does real-time forecasting for end users, but it can also be the search infrastructure that I showed earlier. And our end users interact with this data that feeds back into the source systems. And we have completed the loop. And then we have monitoring and alerting for all components. So not just for the infrastructure components, but also for the data pipelines, also for the data itself, also for data in the data catalog, just monitor, test everything. And then this also becomes a data set with metrics and logs that we can use again. Looks really complex. It can be really complex, but with everything, just start simple. Try to keep it simple. I mean, when I started doing this 3 years ago, we distilled the use case that there was to the bare minimum. We had a very simple use case, basically, but we made sure that we have the correct base, so that we have tests, version control, CI/CD, automated pipelines, stuff like that. And then on top of that, we built our other use cases, and we kept on standardizing. And we were always very pragmatic about that. So don't optimize prematurely. Don't build use cases that you do not know are going to happen. because you might be building something that neither you or nobody else is ever going to use. So build for what you know, and build for what you know is coming in the future, concrete stuff. And develop with care. So like I said before, CI/CD tests, being a good programmer, commenting your code, commenting your data, not just for yourself, because I don't know what I did 2 weeks ago, but also for your colleagues and the people who come after you. Obligatory data landscape picture. The ecosystem of the modern data infrastructure. What you see here already is there's a tool for everything. There's a modern tool for everything that we need to do to get started doing data engineering. We have data ingestion stuff. We have the storage. And here you can see all the big major cloud providers, Amazon Redshift, Google BigQuery, Microsoft Synapse, data lakes, which is basically just blob storage with something on top. We have orchestration. Personally, it's really tiny here, but we use Airflow. It's Python. I like it a lot. We have data quality monitoring as well, so doing data tests. This is actually a really new thing in the data world. Like 2 years ago, nobody was doing data testing, or maybe they were doing it, but they weren't telling anybody else that they were doing it. Data catalog, also very important, with a bit of governance around it. So does certain data hold personal identifiable information? Maybe you should be more careful about who gets to show or gets access to that data. That's an example of having governance. Yeah, and there's also some stuff here. If it's not already too complex or too many pictograms for you, here's another. This is the data and AI landscape as of 2020. I mean, I don't even know half of the stuff that is here, but you have something for anything that you want to do. There's a product that you can use. What I think personally is really nice is this little bit over here, which is open source. And currently, open source data engineering, data analytics is really booming. For everything that you want to do around data engineering, there's a cutting edge open source project with a really cool community around it. So definitely check that out if you want to start implementing data engineering tools. Check the open source stuff that is out there. Then finally, what do I like about data engineering? I like the complexity of working with data. Because it's stateful data, because it is a lot of data, it usually becomes highly complex. You need to aggregate and combine lots of different things. Then you need to check that those things are correct, and then those things also have dependencies, and it's just often becomes a complex problem, and for that you need a complex solution. And that's what I find really interesting. Building a self-describing system, so documenting, automating, anything I like doing as a DevOps engineer, as an engineer, I can also do for data engineering. Data world is moving fast, so I used to think 3 years ago that data engineering was really boring. It's just lots of data and data warehouses and CSV files and Excel and dashboards and reports. But it's actually, there's a lot of stuff happening, and data is becoming more and more important. It's also becoming more and more ingrained in our lives. Because of that, the innovation in the data world is moving very fast. There's a lot of young people doing interesting things with data, around data. So yeah, I really like that a lot. It's multiple disciplines starting to work together as well. So something you might have seen in the DevOps revolution, which started about 8 years ago. We need to work together. Multiple disciplines need to work together. Dev and Ops and the business. Data engineers, data scientists, BI specialists, developers, operations. We all need to work together, talk together, understand each other's problems so that we can build solutions that make everybody better. And that's something I really like in IT. It's about people. It's not just about tech. And I already mentioned this, but data becoming more and more ingrained in everything we do. So there's a lot of purpose there as well, especially around durability and making the world a better place. Data is very important there. Data engineering can help there. That's it.
What an excellent talk, Tim. As I already said, I'm not that technical developed. So are there any questions in the room?
So yeah, I'm just a backend developer, and I was just
I'm
wondering.
also a backend developer.
Okay, yeah, fair enough. But I'm mostly doing like unit tests and submitting a form and displaying something on a page, getting it from the database.
Mm-hmm.
So how does your typical day look like? What is a typical day for you?
Typical day looks like for me. So we have stand-ups because we work agile. We check if we have data pipelines that went wrong. If we need to investigate there, maybe there's a vendor which did not load that data or has like a really faulty API, and we need to say that they suck. But also we have maybe data scientists which have a question about some data or some analysis that they want to do, or they want to maybe use a tool that we have built. So there's some discussions about that, maybe some design sessions around building a new piece of data infrastructure. We personally, we build a lot of tools for our end users to use, and our end users are a lot of data scientists. So we also try to see patterns in the things that we do, and then say, hey, maybe we need to bring these pipelines together, or maybe we need to make them more modular. And then there's usually some time for development as well. And then I try to do some. Currently, I've been working on implementing standardization for our streaming interfaces, so PubSub in Google, and everything around that. So automated monitoring around that whenever we spin up a new piece of PubSub infrastructure. So typical day, some talking, some team building, some designing, and some development, and hopefully not some debugging and production issues.
Okay. Any more questions from the room? Yes.
Hi.
Can you give an example of you were talking about the testing or testing of data? Can you give an example of how you test? Do you use automated testing?
Yeah. So we, as part of our data pipelines, we have data tests. So whenever we move a bit of data around, we test that data, or at least that's something we want to do. We don't do it on all the places yet, but we're getting there. So what that looks like in our case, because you have different data testing frameworks, some of them use Python, so they want to interpret the data as something that's easy to interpret for Python. So for example, dictionaries or JSON or files. We personally use something else called Soda SQL. And like the name already says, it uses SQL for data testing. So we load data into a temporary table. Then Soda SQL tests that data based on a bit of configuration. And the configuration is YAML, because everything is turning into YAML these days. Basically what Soda SQL does is it extracts metrics from that data using SQL. So for example, a certain row count, if there are missing values, because this is something SQL is very good at. But we can also supply more complex tests. So if this field and this aggregation has this range, and this metric is this value, then it is okay or it is not okay. That's also something we can express with Soda SQL. And one of the reasons we have chosen Soda SQL is because most of our data scientists use SQL so that they can write the tests themselves.
Okay, thank you.
Any further questions? Then I suggest we should have a little break, get some drinks, and we will be back in 15 minutes.
Yeah. I mean, if you get any questions later, you can find me here and here. I'm always open to a chat or having an online coffee or whatever, so just hit me up.
Or of course on the Slack channel.
Or the Slack channel. Soon to be. I didn't get an invite yet, but cool. Very cool. Okay, thanks guys.